Bismillahirrahmanirrahim. Assalamu alaikum dear students. I'm Arif and I welcome you all to the fifth video lecture on the subject of computer organization and assembly language programming. The title of today's session is HDL for Combinational Circuits Part 4. Well, today we will start with the concept of these multi-bit gates, that is gates having more than two inputs. For example, AND four-way chip having four inputs instead of two. We will also design the OR four-way as well as the MUX four-way chips. Then we will move on to the concept of buses. For example, AND 16 chip is an AND gate having two inputs, but each input is of 16-bit. That is, it performs a bitwise AND of two 16-bit binary numbers. Similarly, we will also design the OR 16, NOT 16 and the MUX 16 chip. Finally, we will combine the above two techniques and will design multiple input gates with each input as a 16-bit binary number. And we are designing these chips for handling 16-bit numbers because in the later part of the course, the computer we are going to design is a 16-bit computer. And at the end of today's session, we will talk about the explicit and implicit use of built-in chips. We have a lot to do today, so let's start playing. Dear students, suppose we want to design an AND gate chip with four inputs. Although we can design it using the built-in NAND gate, but why to reinvent the wheel? So let us design it using the already designed AND gate chips with two inputs. And if I draw the circuit, it will be something like this. So we have four inputs over here, A, B, C, D. And over here, I'm using the already designed AND gate chip, which will AND these two bits. Then another AND gate chip, which will bitwise OR this intermediate output and this C. And another AND gate chip, which will bitwise OR this intermediate output and this D input. And finally, we will get the output. And which will, of course, having the same behavior, that is, the output will be 0 if any of the input is 0. Or we can say that the output will be 1 if and only if all these inputs are 1. So here is the HDL for this chip. You can see the chip interface having four inputs, A, B, C and D, and a single output. And over here you can see that I have used the AND gate chips that has been designed in the previous session. So this is named as AND four-way. If you want to name it differently, you can, but for this course, let it be like this. AND four-way is an AND gate chip that inputs four single-bit numbers and generates a single-bit output, namely out. In the same fashion, we can design the OR four-way as well, which is OR gate chip designed with three OR gates. This is the HDL. I think it is quite self-explanatory. This is our MUX four-way chip. Suppose that we want to design a chip which having instead of two have four inputs. Four single-bit inputs are coming in, and based on these two selection lines, it is decided which of these four inputs need to be sent on the output of the circuit. Well, this is the table that describes the behavior of the circuit. If the selection lines over here are 0, 0, this A will be placed on out. If it is 0, 1, this B will be placed on out. 1, 0, this C will be placed, and 1, 1, this D will be placed on out. Although we can design this combinational circuit again using the NAND gates, or maybe someone of you might think of designing it using the AND or and the NOT gates, but here we want to design it using the already designed 2 by 1 mux. So this is how it can be designed. Uh, I have placed the 3 mux chips. Each of these 3 mux are 2 by 1 mux. Uh, with these 2 mux, the selection line is common, that is the cell 0. Well, this cell 0 is going to decide which of these two inputs will be placed over here and which of these two inputs will be placed over here. Suppose if I put 0 over here on both of these marks, from this mux A will be placed on this intermediate pin W1, and from this mux this C will be placed. And if I place 1 over here on these selection lines, this mux will output B and this mux will output D. Over here, this is again a 2 by 1 mux, and over here I have placed the second selection line, that is this cell 1. So if I place a 0 over here, whatever is there on this W1 will be placed on out, and if I place a 1 over here, whatever is there on this W2 will be placed on out. This is the HDL of this mux 4-way chip. Observe the chip interface having A, B, C, D for inputs, as well as 2 inputs for the selection lines. For the time being, just ignore this subscript operator, the sort of array operator. You can always have S0 and S1, 2 variables over here. And in the parts portion, you can see the 3 mux chips, 2 by 1 mux, which we have designed in the previous session. We have used these mux chips to design the finally mux 4-way. Dear students, please stop the video, listen this concept again, and move ahead only if you have understood this concept. And if you have queries, please send me an email and let me move ahead. Okay, so now it's the time to practically map these concepts by loading and running these chips on the hardware simulator. Let me move on to the terminal over here. The hardware simulator is already running. Let me load the chip, and from lecture 5, let me load the mux 4-way chip, mux 4-way.htl. Okay, so the mux 4-way chip is loaded in our simulator. You can see the code in this HDL pane. Observe the input pane as well. We have the 4 input pins A, B, C, and D, and the 2 selection bits over here, 0. Let me change the value over here. This is, remember, this is a decimal representation, so I have written a 0 over here. I can write 1, I can write 2, and I can write 3. So this is a 2-bit number. Let me give some values over here. Let me place 1 at A, let it be 0, let it be 0, and let this be 1 as well. So we have 1 at A, 0 at B, 0 at C, and 1 at D. So if I give 3 at the selection line, so that means this D should be placed on the out. So let me run it. You see, the D is placed over here. Let me place 1 over here or 2 over here. So if I place 2 over the selection lines, we know that C will be placed on the output pin. And C will be placed. I feel a bit comfortable on the binary format. It is more better to easy to understand. So click this drop down menu in the format and select the binary. So over here now the things are in binary. If I place R00 over here and I select OK, so we have 00 on the selection line, and now of course this A will be placed on the out. Fine, it's your decision whether to work on this binary format or you want to work on the decimal format. Both are okay. Well, dear students, please do practice the working of this chip as well as the AND 4-way and the OR 4-way chip to have a very clear understanding. And let me fall back to the slides. Okay, so let's move ahead. Let's talk about the concept of buses. Well, dear students, while designing hardware, a lot of times we need to manipulate a bunch of bits together. And it is conceptually convenient to think about the bunch of bits that are manipulated together as one entity called buses. Well, consider this chip AND16 having two inputs, an input named A and another input named B. But the difference is this A is not a single bit input now, this is a 16-bit number. And similarly, this B is also a 16-bit number. So in reality, this chip has actually 16 plus 16, 32 bits, 32 wires feeding into it. And of course, there are 16 wires going out of it. But still, it is convenient to think about it as two numbers feeding in and one number feeding out. And the behavior of this AND is it will bitwise AND these two numbers and will generate the output. If you see the interface is very simple. We have the in keyword followed by A and B. But this time we have a subscript operator mentioning the number of bits this number A has. So A is a 16-bit number and B is also a 16-bit. So this AND 16 chip will operate on these two binary numbers and will generate the output. Okay, so let's see it. So I think everybody is very much familiar about bitwise AND. So suppose the 16-bit binary number A contains this number. I don't know what is it in decimal. And the 16-bit binary number B is shown over here. And this should be the output of this AND 16 gate, which is bitwise ANDing these two numbers and writing it over here. Bitwise ANDing, writing over here. And over here you can see two ones makes the output 1. 2 1 makes the output 1. 2 1 makes the output 1. 2 1 makes the output 1 and rest everywhere is 0. So how we can do that? So it's very simple. We just need to use the AND chip that we have designed previously, but we are going to use 16 different AND chips. The first AND chip will bitwise AND the least significant bit of A with the least significant bit of B and will generate the least significant bit of output out. And similarly, this AND chip will bitwise AND the most significant bit of the number A and the most significant bit of the number B and will generate the most significant bit of the output value out. So here is the code of the AND 16. It's very simple. You can see it has two 16-bit inputs and one 16-bit output, and we have over here 16 AND gates. Because of the paucity of space, I have just mentioned this dot dot dot. So complete this code when you are writing it. So the first AND gate is bitwise ANDing A sub 0 with B sub 0 and placing it in out sub 0. So I hope the code is clear, and let me move ahead. So R16, it is again self-explanatory now. It is just bitwise ORing two 16-bit numbers and generating a 16-bit output. This contains, of course, 16 simple OR gate chips. This is the code. In the same fashion, this is the not 16 gate having a single 16-bit number as input and a single 16-bit number as output. So it's simple. Let me move ahead. Okay, Mark 16. Let me talk about this chip for a while. Excuse me. So this slide is going to show you how we can design a Merck 16 chip. Well, this is a chip that receives two 16-bit binary numbers, and depending on this single bit selection input, it decides whether to put this number A on the 16-bit output or to put this number B on this out. Once again, we just use 16 2 by 1 mux chips with a common selection line, common to all. If there is a 0 on this selection line, all these multiplexer will send the number A on out. A sub 0 will be placed on out sub 0, A sub 1 will be placed on out sub 1, and so on to A sub 15 will be placed on out sub 15. And if we have a 1 on this selection line, which is common to all these 2 by 1 multiplexers, this multiplexer will place B sub 0 on out sub 0, and this will place B sub 15 on out sub 15. And here is the HDL program for this multiplexer chip. You can see the chip interface, a 16-bit number A, a 16-bit number B, and a single-bit selection line, which is common with all these 16 multiplexers, and a 16-bit number out. And in the implementation part, you can simply see there are 16 2 by 1 mux chips that we have used. Okay, so let me touch upon the concept of sub buses as well. Dear students, buses are indexed from right to left. Suppose if foo is a 16-bit bus, then foo sub 0 is the least significant bit, and foo sub 15 is the most significant bit. Moreover, buses can be composed of sub-buses, that is, we can compose a 16-bit bus from two 8-bit buses. And in this code snippet over here, we have two 8-bit buses, namely LSB and MSB. And in the first 16-bit value to this gate AND 16, we plug in the 8 bits of LSB and the 8 bits of MSB. And note this dot dot notation, using which we can mention the sub-range of a bus. Lastly, if you want to initialize an entire bus with zeros or ones, you can do so in one command by assigning true or false to the bus. Okay, now it is the time to practically see these concepts on the hardware simulator. Okay, over here, let me load the chip. Let me load AND16.htl this time. This is the AND16 chip. Let me load this chip. This chip is loaded. This is the code for the AND16 gate. You can see the 16 AND chips, which are bitwise ending 2 bits. And over here they are placing them on out 0, out sub 1, out sub 2, and so on. This is the input pins pane. The format right now is decimal. Okay, fine. Let me place, let's suppose 595 over here, and let me place, let's suppose 49 over here. And now once I will click this eval button, these two 16-bit numbers will be bitwise ANDed, and the output will be placed over here. And the output is 17. Not very clear. Let me change the format to binary. Okay. So now you see this 1 and 1, this makes the output 1, which is of course 1. 1 0 makes 0 0 0 0 0. This 1 1 again makes 1. So we have a 1 over here. And then we do not have 1 on both sides of a specific bit location. So this is it. So the AND 16 chip, this AND 16 chip is working perfectly fine. Dear students, do verify the OR 16 and the MUX 16 chip as well on this hardware simulator at your own time. And let me move back again to the slides. Okay, so now we are ready to design chips having more than 2 inputs and each input of 16 bits. And the first chip we are going to design is the AND 4-way 16. Excuse me. I suppose now we need to build a chip that bitwise and four 16-bit numbers. So instead of two 16-bit numbers, we have first, second, third, and fourth, four 16-bit numbers going inside this chip. We can design this chip using 3 and 16 chips. 1, 2, and 3. 3 and 16 chips, each capable of adding two 16-bit numbers. So we have AND 16 chip, which is bitwise adding first and the second number, 16-bit numbers, and generating a 16-bit output W1. Then this AND 16 chip is bitwise adding the number at W1 and the third number, and generating a 16-bit output at W2. And this AND 16 chip is bitwise adding this W2 with the fourth 16-bit number and generating the final output, which is also of 16-bit. And if this is clear to you, you can easily write the HDL for this chip. The chip interface contains first, second, third, and fourth four 16-bit numbers as shown over here, and a single output out, which is again 16-bit. And as far as chip parts are concerned, I have just used 3 and 16 chips. And the first and 16 chip, I have given the number first, A first, this first number, B second, this second number, and out is W1. I hope the code makes sense to you all. And on the same pattern, you can use do it with the MUX 4-way 16 as well. A MUX 4-way 16 is again a combinational circuit having four inputs, but each input now is of 16-bit, and based on the selection lines, it will generate the output. If the selection line contains 0, 0, this A will be placed over here. If this is 1, 1, this D will be placed over here. So this is the table that shows the behavior of this chip and how we can design it. Well, you can always design it using the NAND gate, or you can design it using the AND, OR, and the NOT gates, but that code will be quite a lengthy code. Uh, Once we have already designed the MUX 4-way chips and the MUX 16 chips, I think that will be much easier to use those chips in this chip. So I'm using 3 MUX 16 chips. This multiplexer will select either A or B and place on W1. This multiplexer will select either C or D and place on W2. And this selection will be done based on this selection 0 bit. That is this one, this bit. Similarly, over here, the multiplexer again use the cell 1 bit, that is this bit. And if it is 0, whatever is there on W1 will be placed on out. And if we have a 1 over here, whatever is there on W2 will be placed on out. I think it is quite simple now because we have come up to this step by step. And if the MUX 4-way and the MUX 16 is clear to you, MUX 4-way 16 is also clear to you. So this is a code in which you can see we have A, B, C, D for 16-bit numbers, and we have two selection lines, and I'm using the MUX 16 chips. Okay, so fine. If you think that you need a MUX 8-way 16, you can always use MUX 4-way 16 instead of MUX 16. This is also, I think, self-explanatory. We are using two MUX 4-way 16, which are selecting the 16-bit numbers. One of these four numbers placed over here, one of these four numbers placed over here. So over here we have now two 16-bit numbers. So we are just using MUX 16 over here. And here is the code. You see two MUX 4-way 16s are used and one MUX 16 is used. Once again, my dear students, if the concept is not very clear, please draw this diagram, repeat this portion of the video, and if you have understood it, then please go on to the demo part. Fine. And 4-way 16, MUX 4-way 16, and MUX 8-way 16. Let me move on to the hardware simulator, and let me load this time MUX 8-way 16. We have the chip of MUX 8-way 16. Yes. So this is the binary view. Let me change the view to decimal. Okay, so now we have these 8 16-bit numbers, and we have the selection lines, 3 bits for the selection lines. We can select any of these 8 numbers based on this selection input and place it over here. Let me place a number 253 over here. Let me place a number 21 over here. Okay, so if I place a 1 over here, so 0 and 1, this B will be placed on out. That is, the out will contain 253. You see, and if I place let's suppose 7 over here, this number, this H16 H number, 0 will be placed over here. This is it. And if I place let's suppose 0 1 2 3 4 and 5 over here, so this 21 will move on to this place. And that is it. Well, I think that is all. If you want to play with it, do make time, play with this, and do load the AND 4-way-16 and MUX 4-way-16 as well, and verify the chip logic that we have written inside the class. Okay, so now let's move on to the concept of built-in chips. Well, a built-in chip has an HDL interface and a Java implementation. So you see this is the interface, HDL interface of MUX 16, two 16-bit numbers and a selection line, and the out, which is also 16-bit. But inside the implementation part, instead of having parts and different gates implementing this chip, you have a keyword built in and then the name of the chip. So this MUX 16 chip is implemented as a MUX 16.class file inside your hardware simulator, the Java class. So all these built-in chips implementation are there inside the tools and the built-in chip directory, which you all must have downloaded by now from the course Bitbucket repository. Well, built-in chips are basically used to implement basic primitive gates to build other gates. And we have seen this as far as the NAND gate is concerned. So the NAND gate built-in implementation is available, and from that NAND gate implementation, we have built the AND and the OR and the NOT and the XOR and the multiplexer, demultiplexers, encoders, decoders, and so on. Similarly, in the coming parts, we will see there is another chip that is the D flip-flop, DFF, and using that D flip-flop, we will be designing different registers and the memories and so on. Built-in chips provide the functionality of chips that the user did not implement for whatever reason. Suppose if you have not implemented some chip and you want to use it, and a built-in flavor of that chip is available, that will of course kick in at that time. Moreover, the built-in chips improve simulation speed and save memory. Uh, Built-in chips implement chips that have peripheral side effects like I/O devices. We will see to this when we will design our own keyboard and screen. Built-in chips implement chips with a feature of GUI used for debugging, and built-in chips can be used either explicitly or implicitly. Well, this explicit and implicit use of the built-in chips are on the next slide. Well, this is the explicit use of the built-in chips. Well, you can load this chip mux16.htl from the built-in directory, tools built-in directory as shown. Once loaded, you can see the HDL pane, the standard chip interface. And below that, instead of parts, keyword, and the HDL code, you can see the keyword built-in mux over here. That instruct the hardware simulator to use the Java class implementation for this chip. Well, this is the explicit use of the available built-in chip, in which we load the chip explicitly in the hardware simulator. Please do that. Please do that practically. The other use of built-in chips is the uh, implicit use. Implicit use of built-in chip. Consider this HDL code for the XOR chip, which is using the not and the or gate chips. Well, dear students, if you have not written the code for these three gates or these three chips, or if these three chips implementation is not there in the current working directory, then instead of giving you an error, the hardware simulator will automatically use the built-in implementation of these chip parts. This is how the hardware simulator explicitly use the built-in chips. So it's really great. It's really great. Oh, well, remember, if you don't implement some chips, you can still use them as chip parts. It is the time when the built-in implementation will kick in inside the hardware simulator. Moreover, remember that a chip cannot be used in its own implementation. That is, you cannot use an AND gate chip while designing an AND gate chip. Okay, dear students, that is all for today's session, and these are the tasks you need to do. First of all, I would like you to perform the testing of the chips designed in today's session. And you can download the HDL file, the test script file, and the compare files from the course Bitbucket repository. And these are the list of the chips that I expect that you have designed so far. If you have not done so, please do that. The first list is this contains the chips for very basic and elementary logic gates. And the second list is basically the multi-way variants. We have seen them today. And the third list is the multi-bit variants. And this last list is the combination of these two lists. Please try implementing all these chips if I have not implemented any of them in my class sessions. Uh, Lastly, if there is any confusion to you regarding the HDL, please do refer to the HDL Survivor Guide available at arifbud.me, my personal website. And remember, coming to office hours does not mean that you are academically weak. I hope today's session was informative for you all. If you have liked it, please share and subscribe my YouTube channel and share it with your friends. I wish you all the best, happy learning, and Allah Hafiz.